Okay, so in this video I'd like to talk about roll center and how you derive it and how you can leverage it to your advantage for setting up your RC car. So here we have once again my vintage Kyosho laser, and let's start by looking at the car from the rear. Okay, and let's look at what we have. We have some internal assembly with a bulkhead, a gearbox, a shock tower. Let's just treat this as one block here, okay? Then I have suspension arms, camber links, and two wheels. So let's illustrate this on a piece of paper to make things a little easier to understand. So here we have our left and right tire. We have our block, right, which is our shock tower, gearbox, bulkhead assembly. We have our lower suspension arms, and we have our upper camber links. And these little boxes on the inside of the tire are the hub carriers. So these 2 points down here correspond to the hinge pins for the suspension arms, and these 2 points up here correspond to the ball stud positions for the camber link. Now the way you would define or derive roll center is to take your suspension arm and your camber link and project out imaginary lines from both of those all the way out to infinity. And at some point in space, those two lines will intersect. This intersection point is called the instant center. Then if I take this instant center and I take the center of the tire, at the bottom of the tire relative to the ground, so we assume that this is the average contact patch location of the tire to the ground. I draw an imaginary line between these 2 points. I do it for this side, and I do the same thing for the other side of the car. Where these two lines intersect is called my roll center. Now you can imagine as the suspension is compressing and moving around, right? So this is compressing here, or maybe the chassis is rolling, or maybe the whole thing is compressing. All these angles are going to change, and that's going to move the instant center around, and that's going to move the roll center around. So right now what I'm showing you is a static case to make the illustration, the conceptual illustration, much more simple. But in reality, the instant center is a dynamic thing, and roll center is dynamic. But let's ignore that for now. So we have a roll center, okay? And we have a center of gravity. This center of gravity is defined by the average distribution of mass throughout the car. So here, let me just move this stand. Okay, so how do I change the average distribution of mass throughout the car? Well, if I have a car design where, say, this gearbox was a little bit lower, or maybe I laid the shocks down, right? On some chassis designs, the shocks have a more laid down geometry, like on the old Schumacher Cat 2000, or if I just very simplistically drop the ride height, okay, what I'm doing there in either of those cases is I'm changing the center of gravity. I'm pushing that down. Or if I just add a whole bunch of weight to the top here for whatever stupid reason, that would push the center of gravity up. Now, the distance between the roll center and the center of gravity informs what is called the roll moment. This is a moment of inertia. What moment of inertia it describes how much, it's like an angular inertia. So if you imagine, or a rotational inertia, if you imagine a figure skater spinning on ice, you'll notice as they pull their arms inward toward their body, they start to spin faster and faster. And the reason for that is because the center of mass, or the average mass, is placed closer and closer to the axis of rotation. Okay, that allows them to spin faster. And it's a similar effect here if you have a low roll moment, so the roll center is high, or the center of gravity is low, or both. The ability of the car to transition from one direction to the next, if you're going left to right very fast, that ability is improved. The car is more responsive, okay? However, if the roll center is low, or the center of gravity is high, so you have a high roll moment, that's going to make the car roll more from left to right, kind of like a pendulum, okay? okay? And as it does so, it transfers more weight to the outside tire under a cornering load. So, depending on the type of track you're on, a high or low roll center may benefit you. If you're on a very high grip track, where you already have plenty of traction between the track surface and the tire, you don't need to roll the chassis to generate cornering grip. So you can move the roll center up and or the center of gravity down. If you're on a low grip track like loose dirt, a classical outdoor off-road track, then you might need a lower roll center to maintain cornering grip mid-corner, okay? So how do I actually change the roll center? Well, we know that the hinge pin locations on the hub carrier and on the bulkhead are fixed. We cannot adjust those. What we can adjust are the ball stud locations on the hub carrier and on the bulkhead, and those will change the instant center. So if I move this ball stud on the bulkhead up, then that flattens out the angle of your camber link. As that flattens out that angle, that imaginary line gets pushed out farther in space, and it intersects with the imaginary line extending from the suspension arms further out and then further down. So now this becomes my new instant center if I move this ball stud up. Now this instant center, if I draw an imaginary line from here back to the tire, you can see that that is at a slightly lower position than the older instant center, so this is going to push the roll center down. So moving this ball stud up pushes the roll center down. Likewise, if I move the ball stud on the hub carrier down, it has a similar effect on flattening out the camber link, pushing the instant center out and down, pushing the roll center down. So basically the effect of moving the ball stud on the inside and on the outside is opposite. Okay, if I move the ball stud on the bulkhead up or the ball stud on the hub carrier down, they both reduce roll center. Likewise, if I move the ball stud on the bulkhead down and or the ball stud on the hub carrier up, those will increase the roll center because that sharpens the angle of this camber link, which pushes the intersection point up here somewhere. So this becomes my new instant center, and then that's going to increase the roll center. Okay. Now, where did I want to go with this? Okay, so now we know how to adjust roll center. One more thing here is, what do you think happens if I take this whole thing, like say I move the ball stud on the hub carrier down and the ball stud on the bulkhead down both at the same time. You would think that because these each have an opposite effect on roll center independently, that if I move them both together that they will cancel out. But that's not exactly true. The reason for that is, again, it comes down to how we derive roll center. If I move this whole thing down, so I move both of these ball studs down, then that's going to push the instant center in and up, and that's going to increase the roll center. Okay? And if I move both of these ball studs up, it has the opposite effect. It pushes the instant center out further and down further, and that's going to drop the roll center. Okay? So this is what roll center does, and it's important to understand it because it plays a very important role in co-optimizing both your roll center and your camber gain. So I have another video where I talk about camber gain, and what happens there is, how you adjust camber gain by moving this ball stud in or out, and then as we see here, you can adjust roll center by moving this ball stud up or down on the shock tower / bulkhead assembly, or on the hub tower itself, right? Different hub carriers have hub towers with different assemblies with different holes in them. Some hub carriers are set up so that the ball studs don't mount in and out like on this chassis, but you can actually mount them up or down. And that's beneficial because if you screw the ball stud in vertically, then you could put spacers under the ball stud to more finely adjust the height, instead of here, where you see on the hub tower here, And on the shock tower, you have very discrete vertical locations for adjusting roll center. Okay, so if the ball stud screws in vertically, you can more finely tune your roll center. And you'll see that on more modern cars like the B5M, for example. Okay, so back to the interplay between roll center and camber gain. If I have a low roll center, and that causes the car to roll more mid-corner, okay, as you know from the camber gain video that I recorded, that results as the chassis rolls more, okay, the outside tire goes to a more positive camber. And I can compensate for that by increasing camber gain to keep the contact patch flat. So, in other words, why would I want to drop the roll center? I want to drop the roll center to cause more weight transfer toward the outside tire, pushing the outside tire down more and generating more grip. So in order to isolate the effect of that increased weight transfer on grip, I need to make sure that the actual contact patch of the tire is not changing. Okay, so if I have a high roll center and it's causing the contact patch of the tire to change as the suspension compresses, I would need to increase camber gain to flatten this out again, and that would allow me to just isolate the effect of the increased weight transfer. So what you may find, it's not always the case, but what you may find typically is if I want, say, a low roll center, I may need to also have high camber gains. So if I want to drop the roll center here, I would increase the ball stud height and then maybe also move this out a bit over here. And if I had a high roll center, so I want to reduce chassis roll, I'd move the ball stud down, and because that results in the chassis not rolling as much, I don't have as much change in camber. I don't need as much change in camber on the tires, so I can move this ball stud in. So you can imagine here, these two boxes are basically imaginary grids, or I can place the ball stud on the bulkhead or shock tower assembly. So over up here, if I move this ball stud up here, this would be a high camber gain and low roll center condition. So the chassis is rolling a lot and the camber is changing a lot, so that mid-corner I have the same contact patch with the tire, but just more weight on the outside tire. And then as I move along this diagonal here, okay, the camber gain drops and the roll center increases, so the chassis rolls less. Because it's rolling less, I don't need as much camber gain to maintain contact patch between the tire and the track surface. Okay, so again, you won't necessarily need to go along this diagonal, but you may find if you change one, say roll center, you may also need to change the other, the camber gain. Okay, so this is what it does for both the front and the rear. The effect on the rear is much simpler because you're only dealing with suspension travel. You're not dealing with any steering at the rear of the car. The effect on the front of the car is a little more complicated because you're also playing around with how the car is steering. Okay, so let's get this around. This desk is a mess, sorry. Okay, so the front of the car, similar concept, right? If I have a low roll center, so say I take this camber link ball stud, I move it up, the roll center drops, the chassis is rolling more left to right. So what would that do as the car is steering? What would happen is, if I have, if the suspension is compressing toward the outside of the tire, so the car is steering to the right, suspension compresses toward the left, okay, there are a few things that happen. The first thing is, if I have, say, a low camber gain, that's going to end up increasing the positive camber on the outside tire. So the contact patch of the tire with respect to the track is changing if I have, say, a low roll center and a low camber gain. So the roll center itself will allow me to have more weight transfer, again, towards the outside tire, but I'm undermining that effect on total traction if I also have low camber gain, because that changes the actual the total contact patch with respect to the track. Now, to compound that, at the front, we also have steering geometry effects such as bump steer and Ackerman. I have discussed bump steer already. I'll get to Ackerman soon. And if I have, say, high bump steer, okay, so as suspension compresses, the wheel starts to turn in more. So I have more turn in, that should give me more steering. And then I have more weight transfer to the outside tire. So that should give me more grip. Combined with the higher turning angle, should give me more steering. But if I have a low camber gain, I can lose contact patch. And so there may be a net reduction in the total amount of steering I have. So the combination of roll center and camber gain together will inform how much total grip I have at the front of the car to get steering for a given steering angle. Okay? So hopefully this is informative enough for you to understand what roll center does and its interplay or its interaction with camber gain and why it's important to look at them both. So that's it for roll center. Thanks for watching.